Bonjour, bon après-midi. Merci d'être avec nous. Je suis Luc Vinet, directeur d'Ivado. Toujours un plaisir de vous voir à cette série de séminaires quantiques. And today we are really thrilled to have Rishi Kondor with us. At Ivado, we try to combine AI and some of quantum. We're really focused on AI. And today the emphasis will be more on the AI aspect of things, even though it will address some, as you will see, some issues that are of relevance also in quantum problems, things like the Clebsch-Gordan problem. So thrilled to have Rishi Kondor with us. He's a professor at the University of Chicago in the Department of Computer Science and of Statistics. Just if I'll try to remember a few salient points of his CV. He did the tri-post at Cambridge, and after that, he did his master at Carnegie Mellon University, his PhD at Columbia in New York. And after having completed his PhD, he did a first postdoc at the Gatsby Institute at University College, where that was founded by Jeff Hinton, most recent physics Nobel laureate. And after that, another postdoc at Caltech. And after that, he took up a faculty position at the University of Chicago. He's a world expert on equivariant neural networks. And will be the topic of his talk. And without any further ado, Rishi, take it on.
Great. Thank you very much. Okay. So as Luc was saying, I'm going to talk about equivariant neural networks. I try to focus both on their potential applications in doing actual physics or chemistry or some certain types of biophysics problems, as well as the underlying mathematical principles, and even how these networks can be efficiently realized in software and on present day hardware architectures. So with that, I'm trying to cover all my bases here in terms of the audience. It's difficult for me to know how many of you have a background more on the science side versus the computing side or the math side. Hopefully, there's going to be a little bit of things of interest to each of these groups in the audience. Okay, so what are, and by the way, if you have questions, please don't hesitate to raise your hand, or questions or comments or complaints, raise your hand and ask questions. It also helps me to kind of calibrate the talk to some extent if I have a feedback event during the talk. Okay, so what are equivariant neural networks? Equivariant neural networks are a class of architectures that bake in certain underlying mathematical constraints into the structure of the algorithm of the neural network itself, in particular, symmetries. So when I say symmetries, I literally mean symmetries in the sense that we talk about symmetries in, say, physics. So symmetries to underlying groups. And these kind of architectures have recently become popular. This has become an independent little field within this vast kind of flood of neural network research, partially motivated by the usual kind of almost like industrial applications of machine learning, like, object recognition and speech and so on, but more directly directed at applications in the sciences, because there these symmetries are just so apparent, and it's so important to respect them. So I'm going to talk about symmetries and equivariant neural networks in the general, but just to anchor your anchor the presentation a little bit in terms of something concrete that you can imagine, let me talk about two specific applications. So one of them is learning forces between atoms, learning force fields to be used in something like molecular dynamics, right? So molecular dynamics is about simulating molecular systems or crystals, that sort of thing, essentially integrating the equations of motion forward, so creating this movie of how the system evolves, and that requires, it's basically a kind of classical physics tool, but it requires knowing the forces between the individual particles, in a simple case between the individual atoms. And classically, these forces okay, so in principle, you could compute the forces directly from quantum mechanics, and that would be forbiddingly expensive. So classically, what people have done is that they designed various kind of empirical force fields, which the way to imagine them is just this relatively simple closed form formulae for expressing the force on a given particle as a function of its neighbors. So that's very simple and efficient, and there's a lot of literature, but clearly it has limitations. It has limitations in terms of what kind of interactions it can reflect and at what fidelity. So there has been a move in material science and computational biology to some extent in recent, maybe in the recent decade, to, instead of using these classical force fields, attempt to learn the interactions between the atoms. And today that usually means learning it with neural networks, but just the way that I described this problem, it's apparent that the problem is going to be subject to symmetries. So it's going to be subject to translation invariance, which is relatively easy to implement, but also rotation invariance, right? So if you rotate the environment of a given atom, then of course the force that that atom experiences also needs to be rotated by the same element of the underlying rotation group SO3, okay? So that's one type of symmetry which falls in and implement, which can be realized by equivariant neural networks, and we'll talk about this at some length. But there's other types of symmetries as well, including discrete symmetries. So another very popular branch of deep learning is graph neural networks. So designing neural networks that either learn from graphs, and here graphs you can think about a social network or a part of a social network or something like that. But again, you can think of something closer to science like molecules, like learning the properties of molecules, right? So you learn something about molecules represented in graphs. So you learn something about graphs, or you learn something that happens on graphs. So for example, you have a function that describes the properties of individual vertices, but that function is related to the underlying graph structure. So in both cases, people use graph neural networks. There is a very large literature on this subject right now. But what's clear right from the outset is that whatever you do with a graph, on your computer, it's going to be represented. The graph is going to be represented as the adjacency matrix, an n by n matrix, which captures the topology. But that representation is not unique. So you can permute the vertices and it's still the same graph. So here you have invariance with respect to the action of the permutation group, the so-called symmetry group, acting on this adjacency matrix or anything else that's related to the vertices or the adjacency matrix. So the nice thing about mathematics is that it can provide us very general tools which are applicable across a wide range of different instances of an underlying phenomenon like symmetry. So in this case, this equivariant neural networks actually will be able to encompass both these cases and many others. Okay. All right, so now one slide to jog the imagination of people coming more from the mathematics side. So what I'm going to be talking about is equivariance with respect to actions of groups, which is from a mathematical point of view means something akin to a commutation relationship. So the action of the group, like the symmetry group, commutes with the action of the neural network or the individual layers of the neural network, or more technically, they don't commute, it's an intertwiner. And the other thing that I talked about before is invariance, where what the neural network does is actually invariant to the action of the underlying group. But clearly, invariance is just a special case of equivariance. So we're going to be able to encompass both of these cases kind of with the same machinery. All right. So the nice thing about this formalism is that it applies to not a wide variety of types of neural network architectures that people use today. But for the sake of just exposing the subject, it is probably best to stick with the simplest possible thing, which is one of these classical kind of convolutional type neural networks, fully feed-forward architecture, which takes an input and then applies a sequence of transformations. So these are called the layers of the neural network. At the end of the day, or at the end of the sequence, it produces an output, which is kind of what we want to predict. And in this kind of very simplistic view of simple neural networks, usually the pattern is that you have this alternating sequence of linear transformations and nonlinearities. And the linear transformations are also the place where the learnable weights, so the parameters of the neural network are. And the nonlinearities are often something very simple, like just this kind of ReLU function that is very popular today, okay? So this is the kind of architecture that is best to start out with. How does equivariance manifest in this case? Well, first of all, it's important to know that in the neural network, field cats are very important. It's like the, so everything needs to be explained in cats. So the situation in equivariance is that the input cat suffers a transformation under the action of the underlying group. So the input cat gets, say, rotated. And then if the neural network is equivariant, then the internal representations of the cat, so the outputs of further layers, also transform. But the important thing is that they are covariant with respect to the group. So that means that we know how they transform. They transform in a very controlled way. And that's important because first of all, it's important if we want to have a covariant cat as the output, but it's also important if we just want to have something invariant, like just the word cat, because we recognize the cat. It's still, in order to build sufficiently powerful invariant architectures, usually the best way to approach the problem is to have an architecture which is equivariant on the inside, and at the very end, you kind of symmetrize over the group. In the top layer, the readout layer, you do something which kind of mods out by the last action, and you get something invariant. So the morale of the story is that both invariant and equivariant learning tasks in general require equivariant architectures on the inside. And this kind of feed-forward architecture is the simplest case, but we are going to be discussing that problem at the level of individual operations. So like today's neural networks, they are like this, right? They're this kind of a complicated mess of various types of operations, sometimes pretty expensive operations, which finally result with something at the top, and then you backpropagate gradients and so on and so on. But there's people's imagination has proved to be unlimited in terms of what types of architectures they can dream up. At the end of the day, the only thing that you need from the architecture is that for the individual operations need to be differentiable so that you can do backpropagation. But the network can be kind of as complicated as you want. Now we have this extra constraint that it also needs to be equivariant. So what I'm saying is that I'm going to be talking about how to construct individual components of neural networks, which are themselves equivariant. And then if you build a neural network out of equivariant components, i.e. equivariant, these generalized neurons, then the entire thing is going to be equivariant. So at the level of these individual units, the individual little neuron, equivariance just means that if every input of the neuron transforms in a specific way with respect to the group, so we know how the first input transforms in the second and the third, then we know how the output is going to transform. the question is, for the rest of the talk, basically, the question is how to realize this constraint directly in the architecture so that there's going to be no choice. Whatever the neural network does, it's going to be learning an equivariant sequence of operations. Okay, so now you notice that I wrote the action in this way. So this is just a general way of saying that a group element G transforms the individual inputs. But in reality, basically with a slight exaggeration, every single paper that I've seen in this field considers linear actions. So if the action is, for some reason, you have an action that is not linear, usually you can still reduce it to the tensor product of linear actions. So really what we need to focus on is just the linear case, okay? So now those of you who are familiar with representations theory are starting to get the gist that this is where all this is leading. It's leading to talking about representations of the group and reducing things into irreducible representations and formulating these equivariance conditions in terms of these irreducible subspaces and so on and so on and so on. So for those of you who might not be familiar with just this general concept of representations, here is one slide where I try to explain the high-level idea. So a representation of a group G is, a homomorphism into the general linear group. What that really means is that it's a mapping from the group elements to matrices. And the matrices multiply the same way as the group elements do, okay? So this is wonderful. It's really useful for understanding the structure of the group and for whenever the group is acting on something, is actually doing something on other vectors. But another way to think about it is that all that we're doing here is we're modeling the group, right? So the groups are fairly abstract mathematical objects. It might be difficult to even write down what the group multiplication rule is, what it implies about the structure of the group, and so on and so on. And this idea of representations is just to replace the group elements by matrices. The matrices behave the same way as the group elements. So this is like a more kind of down-to-earth model for the group. Okay, and as such, mathematicians spend a lot of time or have expended a lot of effort into studying representations of specific groups, figuring out what representations are possible, how they're related to each other, and so on and so on. So this theory of equivariant neural networks really just piggybacks on this really well-developed branch of mathematics. Okay, so I'm going to try and avoid talking too much about the mathematics and cut to the machine learning as much as possible, but we need a couple of basic concepts, in particular concepts about what these representations might be and how they might be related to each other. So for example, one thing you notice very early is that if you have one representation, okay, first of all, I should say, I always forget this, that by default, I'm always talking about representations over complex numbers because that's the easiest thing, but we can go into that separately, but by default, everything is over the complex numbers. So if you have one representation rho and you just take a fixed unitary matrix U and you conjugate that representation by U, then you get another representation. But this is it's not really a new representation, right? So it's really just the same representation on a different basis. So this is almost like cheating, right? So this is not, I'm not going to consider these as like really separate representations. Another thing is that a representation might break apart into a direct sum. So this kind of block diagonal combination of other representations after, once again, conjugation by unitary matrix U, okay? So this is, again, a common situation, but this new representation is not really going to be telling you anything new beyond rho 1 and rho 2. It's just like a trivial combination of these rho 1 and rho 2 representations. So the real interest in representation theory is finding the elementary building blocks, these smallest possible irreducible representations that you can build up all other representations from. And here is another crucial concept that comes in, or another crucial constraint, and that is of all possible groups that we could be looking at, the class of of finite groups and compact Lie groups. So compactness is important because some fundamental theorems of representation theory tell you that that any finite dimensional representation of a compact group can be reduced into a direct sum of the irreducible representations of the group. So that means, so that kind of reinforces that this basic fact that there are these things called the irreducible, the smallest possible representations for a given group, and it's really sufficient to focus our effort on just these irreducible representations, because everything else is going to be kind of built up from these irreducible representations, generally in a fairly simple way. So most of the effort in understanding the representations of a given group is directed at just the irreducible representations. So correspondingly, equivariant neural networks also deal with the irreducible representations. They try to capture data and underlying symmetries in terms of these irreducible, kind of smallest possible representations of the group. Okay, so now we are at the point where here's what was on the previous slides is like pages 1 to 9 of your representation theory book. Now we are on to page, say, 13. Okay. And we have another result, which has this deceptively modest name called Shor's lemma. So let's just try and understand what Shor's lemma said. It's directly related to these irreducible representations and how things transform in terms of irreducible representations. So Shor's lemma says that if you have a vector which transforms according to one irreducible representation of the group, and there's a linear transformation that you apply to this vector, and you know that it takes it into another vector that also transforms according to an irreducible representation, say rho dash, then either the map is just the trivial map, just collapses everything to 0, or actually these two representations are the same irreducible representation, and the map is just the multiple of the identity, okay? So you can see where this is going. I mean, we are trying to construct equivariant neurons, and the philosophy is that everything, the inputs and the outputs of the neuron are going to be expressed in terms of the irreducible representations of the group. And this is an equivariant map now, and I've just told you what it needs to look like. So if the neuron takes a number of different kind of like vectors transforming according to different irreducible representations, then you're not allowed to mix them because that would break equivariance. Further, even for a single irreducible representation, the form that this map needs to take is very constrained. It must just be a multiple of the identity. Okay? So this is, for those of you who have a physics background, this is not a surprise. These are the irreducible representations of, say, SO3 or SU2 are intimately connected to angular momentum, and you know that different angular momentum states don't mix, and so on and so on and so on. It's exactly this sort of philosophy that underlies the construction of equivariant neural networks as well. So this is what I just said, right? So, okay, we are trying to construct an equivariant neural network, an equivariant neuron. It's going to have a linear part, and it's going to have some sort of nonlinearity. And I basically just told you how to do the linear part, right? You take the inputs apart according to the irreducible representations of the group. You look at what the output decomposes, which irreducible representations, and the linear part is only allowed to mix parts corresponding to the same irreducible representation, and only mixes them by multiplication with essentially with scalars. So these scalars corresponding to how much of this gets into there and how much of this gets into here and so on, those are potentially learned parameters of the neural network. But these are the only parameters that you're allowed to have. Otherwise, you would break equivariance. Okay. So another nice thing about this scheme is that this process of breaking something that looking at vectors corresponding to the same linear transformation, and then forming linear combinations of them in the general possible way, has a name, and that's matrix multiplication. So imagine that you've just done this. You took you've decomposed the input into, according to irreducible representations, all the little vectors that transform according to the same irreducible representation, you stack into a matrix, and, sorry, this matrix, and then you consider linear combinations of the columns of the matrix. This does the same as multiplying the matrix from the right by a weight matrix, and that's going to be your output. So we took this fairly abstract problem of equivariance to a group. I haven't even told you what the group is. Something that is related to the structure of the group and seemingly requires knowledge of algebra and so on, and something that is not generally, something that neural networks, and in particular neural network software, is generally really bad at. And we reduced it to matrix multiplication, which is kind of the operation that actually computers, and in particular Pytorch and JAX, are pretty good at. So this is efficient, and it's easy to express, and it is guaranteed to satisfy equivariance. And in fact, it is the only type of operation that is guaranteed to, that satisfies equivariance to our underlying group. Okay, so so this fact was, I mean, there are several groups working in this field, and it was recognized by multiple groups. We also wrote a paper on it, which kind of laid this out very compactly, and in particular appealing to the underlying representation theory and underlying harmonic analysis ideas to some extent. Okay, but I'm talking about equivariance to a set of transformations, the class of all possible linear operations that satisfy this quantity. I'm sure that some of you are thinking that this sounds familiar. There's a name for this type of operation. It is convolution, right? And that is the case. So in the classical case, say, think object recognition in 2 dimensions. The holy grail, especially in particular in the neural networks field, going back to at least the late 80s, think of Jan LeCun's early work, for example, but in actually maybe even further, the work by Fukushima, for example, is to come up with an architecture which respects symmetry with respect to translations. So translating a function on the real line or in Euclidean space corresponds to that operation. And clearly, one type of classical signal processing tool which satisfies this property is just classical convolution. So most current image recognition pipelines are built on this convolution idea. They actually implement this formula for convolution inside them, because this is if you plug in, you can immediately see that convolution is equivariant with respect to translations. If you take F and you translate it, since this operation is almost like pattern matching, right? So you have F and G comes along, which is your little filter, your pattern that you're trying to match it and match against it, and you try it at every possible location. Of course, if you translate F, then you're going to have the same matches, but at the translated locations. So this is what the equivariance condition really just tells you. So there is a direct, it doesn't take much imagination to also write down the group equivalent of this. So translation becomes what you see up there. So the subtraction is multiplied, it's replaced just by the group operation. There's a natural generalization of the concept of convolution to the groups. The only thing that might cause confusion is what do you integrate against? You integrate against the Haar measure of the group. That's the classical measure. And that also satisfies equivariance. So we know that in the classical case, convolution is the only operation, is the most general type of operation which satisfies equivariance to translations. And what about this type of convolution on the group? Okay, and how does this match with what I said earlier? Well, it turns out that the two pictures match perfectly because what I described before in terms of irreducible representations and mixing the different irreducible components and matrix multiplication is basically exactly the same story. It's the same operation except expressed in Fourier space. So again, this can be done more explicitly. Maybe I should skip some of the details. So there's a natural way to define Fourier transformation on compact Lie groups. There's a natural way of even extending it to the case where the functions are defined on not the group itself, but on something else that the group is acting on. This is what brings in these arrow symbols. I don't need to skip some of the details here. And then it's possible to prove that actually the necessary and sufficient condition for a linear operation on a function on one of these homogeneous spaces to be equivariant is that it be of this convolutional form. So, you know, in terms of what we're seeing here is that in terms of at least the linear part of the operation that we want to do in equivariant neural networks, the things click perfectly. So we have a perfect generalization of the classical case. So same concepts like Fourier transformation and multiplication in Fourier space and so on come in. And it actually is fairly straightforward now to generate these equivariant architectures. You just need to follow this pattern. Okay, but now how about the nonlinearity, right? So a neural network composed entirely of linear operations is not very interesting because then the entire neural network will be linear and it's not going to do anything surprising. So somehow we need to kind of sneak in nonlinearities as well, but then those nonlinearities also have to be equivariant. And Shor's lemma is not going to tell you how to do that by itself, okay? So it turns out that this is the point where there's a little bit of a divergence in the literature, and people working in different domains or in different architectures have proposed different solutions. The one thing that you can always do is you can always go back to kind of the time domain, right? So you started out by, you know, function in Euclidean space, and you want to learn something about it that's invariant to rotations, or a function on the sphere, and again, you want to be equivariant to rotations, or something related to permutations, but you can always go back to, you know, the actual vector or matrix that the group is permuting. And then once you are back there, then you apply your favorite pointwise nonlinearity, so the hyperbolic tangent or the ReLU or whatever you want, and actually it's going to be equivariant. So that's possible, and there are reasons to do this, but one thing that is apparent is that this is going to require essentially a forward and a backward Fourier transform at every layer of the neural network. So that has an associated cost. And it turns out that in the classical case, you would use a fast Fourier transform. There's a rich literature on that. It turns out that there actually are fast Fourier transforms for various non-commutative groups as well. This is another kind of exciting branch of computational mathematics. But you know, it's still not easy, right? So it's still chances are it's still going to end up being the most expensive operation in your entire architecture. The other thing is that even just figuring out what you're doing, what you're transforming to is not necessarily so easy in the case of these Lie groups. So you're transforming, you need to represent a function on a Lie group or a homogeneous space of a Lie group, okay? You take the simplest possible case, you know, like SO3 and a sphere. So even on the sphere, there's no way of creating a regular grid that covers the sphere without singularities. So there are going to be numerical issues. There's going to be like inconvenience of having to even constrain these grids and so on and so on. So it has a potential, this has the potential of becoming complicated. Okay, but still, so this is the first approach. The second approach is to bring everything down to scalars. Okay, so you have these equivariant quantities. You can create scalars from them. If you just create scalars and that's all you have, then you lose all the group action relative information, so that's not good. But one of the trends currently in deep learning is to look at attention and various corollaries of this concept, which is essentially this kind of multiplicative type of structure where you learn weights and multiply your activations by them. So you can learn these equivariant scalars and multiply them back into invariant scalars, multiply them back into equivariant quantities. That is another possible approach for creating equivariant neural networks pursued by some fraction of the community. I think the most general way, however, is to actually create the nonlinearities in Fourier space. And that's what I want to talk about now. So what if you just insist on staying with these equivariant or covariant quantities, however you want to call it, you insist on staying in the space of irreducible representations. How can you still create something that's equivariant but nonlinear? Okay, so again, back to the simplest thing. So think about the ReLU. The ReLU is great for many reasons, but essentially what we're doing here is this form of Fourier analysis. The Fourier transform of the ReLU is a complete mess, right? It activates all these high frequencies. It's expensive to compute, numerical error, whatnot. So let's do something a little bit modest. Let's start with polynomials. So say I have two vectors transforming according to a particularly reducible representation of SU2, and I try to form a polynomial, multiply them together element-wise. What do I get? I get something that's a total mess in terms of the group action. So that doesn't work very well. But what is the next simplest thing that you can do? And that is to take the tensor product, right? So if you have two vectors, say VA and VB, which transform according to the corresponding irreducible representations, rho A and rho B, you take the tensor product, then that's going to kind of transform according to the tensor product of the representations. And it's very easy to see that the tensor product of two representations is also representation, okay? A bit of a problem is that in general, it's not an irreducible representation, right? Everything in our neural network is going to have to be brought back down to the level of irreducible representations. But, you know, a couple of slides ago, I just told you that on a compact Lie group, any finite dimensional representation can be reduced into a finite direct sum of irreducible representations. So why don't we just do this? So there's a name for this operation, and okay. And that is called the Clebsch-Gordan product. So this is again something, so those of you who have a background in physics are very familiar with, in the probably in the specific case of SU2 or SUN or SO3. So those classical cases which are most frequently encountered in physics. They are encountered for good reason, because it's the fundamental way that you couple different quantities transforming according to in different ways according to the underlying symmetry. But actually, the idea of a Clebsch-Gordan product really applies to any Lie group, at least any compact Lie group, and also any finite group. So it's just this, right? You take two irreducible representations, rho A and rho B, and we know that somehow it has to reduce into direct sum of irreducible representations. Figuring out how many copies of each irreducible representation crop up can be a little bit difficult, but for the groups that we usually deal with, it's actually known. And there is this basis transformation, the C matrix, which is again might be kind of hairy to compute the first time round, but it's it's like a universal constant, right? So it's a fixed matrix that you only need to create once and for all, and then you can use it. So actually, this type of Clebsch-Gordan product nonlinearity is widely used in equivariant neural networks, specifically those networks which people use in this kind of physics, chemistry, this sort of setting. So as far as I can tell, the first time that this was proposed was in this tensor field networks paper in 2018, mostly motivated actually by heuristic ideas, but then it was kind of formalized, and and the whole sequence of further architectures came up using some variant of the same operation, which is again not because there's something so original in this idea. It's just that the mathematics kind of guides you into this. So this is the natural way to create nonlinear functions that are equivariant and expressed in terms of the irreducible representations of the underlying group. Okay, so this is kind of standard technology now in a large chunk of neural architectures, specifically those that are used in physics computations, and it results in these sort of neurons, right? So there's the linear operations, there's super simple, and then there's this basically one extra component that you need to somehow put into your software that might not be there to begin with. Okay, so let's see, how do I economize with my time? What is the best way? So there's also stuff I could go on about how to compute this for the SO3 case in particular, but that's not necessarily what you're most interested in. The resulting architectures can be surprisingly simple. So for example, we did write a paper about using this for spherical object recognition. So think about like 360-degree cameras or something similar. You want to make sure that you recognize the objects equally well, no matter where they are in your visual field and what orientation. And literally, the architecture just boiled down to the combination of of these types of operations, the Clebsch-Gordan product, which mixes these different parts of the input, and multiplication by weight matrices. So as neural network go, this is actually super simple. Similar things, similar spherical CNNs were proposed by Taco Cohen, Geiger, Kohler, and Max Welling a little bit earlier, but without the Clebsch-Gordan product actually, and even people in the computer vision community had been looking at these sort of harmonic analysis ideas and representation theory ideas going back a couple of years earlier, in particular Christos's and Elis's work. Okay, now what about modeling physical systems? So for this, when we came, our version of this kind of force field learning network came out in 2018 after the general results. So instead of the actual architecture, which I have mixed feelings about because it turned out a little bit more complicated than I would have wished. So I think that's, there was maybe an easier way of using the Clebsch-Gordan product to get something that performs well. Well, I think let me stress another component of, or another aspect of this whole approach, and that is that you're enforcing equivariance in Fourier space. So you are guaranteed that the underlying symmetries, possibly the underlying conservation laws, are strictly satisfied. But what else are you doing? So you're creating a neural network which essentially just learns a polynomial expression, right? And the polynomial expression is made up of very simple operations like matrix products and so on, plus this Clebsch-Gordan operation. And that's exactly how physical laws look in the first place, right? So you'd open your electrodynamics textbook and you look at the interaction between monopoles and dipoles and quadrupoles and so on. They look a little bit more complicated, but when you actually think about why they look that way, it's because they involve quantities corresponding to different irreducible representations of SO3 or SU2 and how they might interact, because the potential between two quadrupoles at the end of the day still needs to be a scalar, so that puts constraints on and blah blah blah. So what I'm trying to say is that an additional advantage of equivariant neural networks based on the Clebsch-Gordan product and these equivariant linear operations is that they are biased towards the types of physical interactions that are actually captured in physical laws. So maybe they can more faithfully learn the physics than throwing a bunch of radius together. And possibly they're also more interpretable because you can bring things down to like physically sensible quantities. Okay, so the title of the talk was computational aspects of the equivariant neural networks. And so far I have said almost nothing about computation. despite the fact that that's like an equally important part of the work done in my group, because we found that it's one thing to create the theory for something like that. It's another thing to convince people to actually use these architectures and to help them apply them to their problem, and also to some extent guard against things going wrong. So we've got this kind of software architecture. The idea is to be able to write neural networks in your favorite framework like PyTorch or maybe JAX or something similar, and then have intermediate layers which are designed both for ease of use but also performance, and ultimately bring things down to the level of CUDA, so something that runs directly on the GPUs and allows you to efficiently implement these things in software. Okay, so when writing software, there are these two simultaneous goals. One of them, the obvious, is to create something that allows that is performant. The other is to find the right abstractions so as to make it easy for people to express their ideas in terms of the software, and also hopefully guards against things going wrong. In particular, in our case, equivariance being violated. So the abstractions that we use in our SO3 equivariant library is that of SO3 parts and SO3 vectors. So SO3 parts are these individual matrices capturing the little vectors of the activations corresponding to the different irreducible representations. And the SO3 vec is just a combination of these SO3 parts corresponding to different SO3 vecs. And then you can directly, so these are, the objects in the library. You can directly initialize them randomly or according to some known distribution or from data, and you can operate on them, and you can do all the operations that satisfy the equivariance constraint, and you're not allowed to do things which would violate it. And then there's this extra thing, the magical ingredient, the Clebsch-Gordan product, which needs to be implemented with care, because in reality, that is the bottleneck, right? So it's easy to kind of write down on the screen, just take the tensor product and hit it by a big transformation matrix. That's fine, but in reality, when you're building a neural network, one of the chief constraints is just, first of all, you need to store intermediate results for the backpropagation, right? And typically, you have a large number of channels in your neural network, and you might have a large number of layers, and you're batching various things together. And the constraint that you're constantly fighting against is the size of the memory on your graphics processor unit. So taking tensor products of stuff just so that right afterwards you can hit it with a matrix and reduce it to something smaller is the last thing that you want to do. So that's not how you do this operation. You combine it into a single kernel. And okay, so there are variations on this depending on the structure of what you're multiplying together. You need to be mindful of this, or rather the software needs to be mindful of it. What's nice is to be able to just say, CG product U and V, and all this happens under the hood, gives you the answer without having to worry about what went into trying to write the backend for it to be efficient. So the types of optimizations that we're allowed to do when we have a specialized library for this are avoiding materializing these intermediate results, take advantage of the specific form of the Clebsch-Gordan product. In particular, again, especially for those of you with a physics background, I mean, these vectors correspond to behavior under essentially rotations, or the group SU2. So it corresponds to angular momentum. So you can talk about, so particular dimensions of the vectors correspond to different angular momentums around the z-axis. So obviously that itself is constrained. So there is a very stringent sparsity constraint on the transformation matrix itself. So these C matrices that you multiply with have actually are are quite sparse, and they have a very specific sparsity pattern. So the software needs to directly reflect that rather than as just treating it as generic dense matrices or a generic sparse matrix. Okay, so that's why we needed to write, specialized kernels just for this operation. And then there is the thought about how to parallelize this over the different columns and multiple vectors and batches and so on and so on. And it gets even more interesting when we consider, oh, sorry, this slide was duplicated, yeah. When we consider higher order products. Okay, so by combining these computational tricks, we get a speed up of an order of 10, which kind of matters when you actually want to use this for real world simulations. Okay, this is about higher order products, which is an even more interesting topic, but maybe in the interest of time, I'm going to skip that. Okay, so my understanding is that I have about 10 minutes left. Is that correct? Okay. So this is the second half of the talk. Maybe I'm not going to go into too much detail in this part. So one of the things that I find really gratifying in this line of work is that it encompasses all these seemingly different domains. So far, I talked about groups in general, but I strongly implied things like equivariance to SO3, SU2, and maybe SUN, and then so on and so on. The Lorentz group, which is what we did the work on, and that sort of thing. But actually, so basically the same sort of issues, the same sort of solutions come up in a very different domain as well, the graph neural networks, right? So graph neural networks are one of those subjects that people can get opinionated about. The different, like you can call lots of different things graph neural networks, but to different people, different aspects of it are important. So let me just kind of give you my high-level take on what makes a graph neural network a graph neural network. Okay, so the non-negotiable part is actually the equivariance part, that you're learning something from the adjacency matrix. And there's a natural action of permutations of the adjacency matrix, and ultimately you want to be invariant with respect to that. So I'm talking about the case when you're learning from the graph, right? So if phi is your entire neural network, then it needs to give you the same result for the original adjacency matrix or its permuted version. Okay, so this is why the equivariance ideas come in. But graph neural networks are a kind of more tricky subject because it's overloaded with all these other expectations as well. So for example, usually or often, it's critical to be able to identify specific local features or be able to, for the neural network to be able to pick up on, like individual functional groups in a molecule, right? So you want to have a notion of some way of capturing the entire molecule, but also you really want to have almost like make all these almost binary decisions. Is this functional group there or is it not there? Okay. So ultimately, the best thing would be to have a true multi-scale hierarchy somehow hidden in this representation of the graph. To be able to talk about the graph at the level of small parts and how the small parts relate to each other and how those larger parts relate to each other, finally talking about the overall structure. Does the graph look more like a linear structure, or is it kind of a tangled mess, a hairball or something, right? So creating an algorithm which can capture for general graphs all these different levels of structure and how they communicate with each other has proved not to be so simple. And the final thing is that, okay, I talked about equivariance and how realizing equivariance on graphs is not necessarily so easy, but there are parts of graphs which look very familiar and actually look much more structured, right? So for example, here's a 6 cycle, and say if you look at graphs of organic molecules, they're full of 6 cycles and 5 cycles. So in these locally, you kind of know how you would recognize structure at different scales and be able to respect equivariance. But how do you stick all these different parts together so that globally you are achieving these goals as well? Okay, so the reason that the literature on graph neural networks is so diverse and so active is because it's not easy to bring all these things together. And two types of ideas that have persisted over the years are either to do something starting from the top, i.e. starting from spectral graph theory ideas. So take the graph Laplacian, look at its eigenvectors and do something with that, a kind of Fourier transform on graphs. Or what has actually become more popular is to do message passing. So message passing forgets about all the sophisticated spectral graph theory literature and instead says that what I'm going to do is I'm going to set up this kind of communication system on the graph where the vertices become the neurons and the neurons communicate with each other, but only with neurons attached to neighboring vertices. And they communicate in a very specific way, namely that in each layer, each neuron collects information from its neighbors, sums it, and then does the usual neural network thing of, apply a linear transformation and the nonlinearity, or maybe a multi-layer perceptron, and so on and so on. So this message passing idea has become extremely popular. It's clearly equivariant because there's nothing here that explicitly involves the numbering of the vertices or something. But two things are readily clear about it. One of them is that it only kind of implicitly takes advantage of the structure of the graph, or takes into account the structure of the graph, right? So you're not actually incorporating any structural information directly about the graph. It's just that your communication strategy for your neural network somehow reflects the graph. So that's a very indirect way of reflecting the graph. The other thing is that in each step, you're just summing the inputs from each of your neighbors. So there's a reason for that, is that if you did something that distinguished more between your neighbors, then that might break equivariance. But at the same time, this means that as soon as you've collected information of your neighbors, you kind of forget of what came from where. So people regularly call this a type of convolutional neural network. And it's sort of like a convolutional neural network. It's sort of like classical convolution on images, if you think about that as data encoded in the regular grid. But it's like convolution with filters that don't know the difference between left and right and up and down, like spherical filters. So there are inherent limitations in this, okay? So and I think another interesting direction of research, something that we've been trying to contribute to, is how to make these sort of architectures more expressive. So how to learn information about local domains in the graph in such a way that you still maintain information about the identity of the vertices, maybe even a better representation of the local structure. But overall, when you stitch it together, then you still end up with something that is globally equivariant. So many of these works go in this direction of subgraph neural networks, where different subgraphs, instead of vertices sending messages to each other, it's going to be different subgraphs sending messages to each other, in particular in a way that respects permutation equivariance. Okay, so I guess that the details of this would be a separate talk, but let me just flash some of your, so that you have kind of scalar or vector or matrix valued activations of these subgraphs. And then the question is, how can they communicate with each other in such a way that it's all equivariant, blah, blah, blah. And, okay. And I mean, the long story short is that you could kind of shoehorn it into the same framework that I was talking about in the first half of the talk. So you can talk about irreducible representations, but irreducible representations of the symmetry group, and linear transformations there, and maybe even Clebsch-Gordan products, and so on and so on. But there's another way in this case, which in particular was first, okay, let me just skip ahead, first proposed, yeah, this is the fun way, fun and complicated way. with the irreducible representations of the symmetry group. Uh, but the other way is to do einsums. Okay, so the other way is to say that actually what we really have are just vectors and matrices and tensors that whose rows and columns get permuted by the symmetry group, and if you look at transformations of this form, so you look at these little operations corresponding, just take rows or just take columns or just take diagonals or take slices and then broadcast them to parts of the output tensor. These, what I'm describing, are exactly those kind of operations which are captured by, this generalized einsum operator in the most neural network software. Then if you enumerate all possible ways in which you can perform these linear operations, actually they are going to span the space of all equivariant linear operations in this case. But the correspondence between these two pictures, so the correspondence between the representation theoretic way of answering finding the equivariant operations and this more kind of practical Einstein summation-based way is kind of an interesting topic and potentially something that's worth looking into more. Maybe this is the point that I should stop, and I can take questions. Thank you.
Je pense que lui.
Thank you very much, Risi, for this great overview. We'll be tempted to invite you a second time to get the graph part. Are there any questions? Yes.
Thank you. Thanks for the great talk. I had a question about the computational aspect. When you mentioned the tensor product will be the size of the vectors after the tensor product will be too big, so you cannot handle it computationally. So my question is, have you tried the tensor decompositions? Because after that you have a matrix multiplication, so basically you can have a third order tensor and then a tensor decomposition. Have you tried this aspect?
Yeah, so the easy thing is to fuse the tensor product with the okay, so there's the multiplication with the constant matrix, that Clebsch-Gordan matrix. Is that what you mean?
I think so, because after that you had a matrix multiplication.
Yeah.
Using the dimensions. So I was wondering, it makes sense to have a tensor decomposition to reduce the computations. And but I'm not sure what
you mean something like SVD or something? Or principal component analysis, that sort of thing?
Yes, but on the...
No, so I'm not sure about, I'm not sure about that because there's no indication of low rank structure here. What I was trying to say is something simpler, right? So if you look at this expression, this looks like a tensor product followed by a matrix multiplication. So you can literally do it by, tensor product operation in your software followed by a dense matrix multiplication operation. The better way to do it, and the way that our package does it, is to just write a specialized routine which does this operation explicitly with loops. And that tensor product is never materialized. You just multiply as needed. You multiply the components of those matrices together. So you kind of unwrap this linear algebra operation into loops and scalar operations on the components. That's all. And then if you are more ambitious, then you can actually fuse it with the downstream operation as well, right? In general, this operator fusion is a standard thing in high performance computing to accelerate computation.
Some other questions?
Thank you for the very good talk. So I'm wondering what you think of maybe some of the recent sentiment in the machine learning community that maybe you don't need all these inductive biases the bidder lesson idea that maybe you don't need equivariance and all of that. What's your take on that?
Yeah. I think that this
or Risi, maybe before you start answering this more fancy question, and part of the answer, I suppose, you did not stress what is the use of making the neural networks equivariant. What good is it for,
right. I didn't make
computation times or something.
Right. I didn't. Right. Exactly. So so it really depends on what you're trying to do. So if you're solving the types of problems that these large companies are largely interested in on a industrial scale, like something really like fundamental to humanity, like recognizing cats in YouTube videos or something, and you worry about the rotation invariance of cats, then there's so many videos and there's so many confounding factors. And in addition, actually upside down cats are much less frequent than cats that are the right way up. And maybe doing a little bit of error in terms of recognizing cats is not so tragic. So I understand if you don't want to use equivariant neural networks in that case. I think the assertion would be that things are a bit different when you're trying to solve a scientific problem. So one difference is that the symmetry properties really are there. The other difference is that you might not have such incredible amounts of data. So you want to be as economical as possible as you can be with the data. And in general, every time that you take an extra symmetry into account, you reduce the amount of data needed to train an algorithm to the same level of accuracy. But there are two more things which are maybe even more important. One of them is that if you're serious about doing physics, then you don't just want invariance to these Lie groups in a kind of more or less kind of way implemented. You really want to make sure that actually, angular momentum is conserved and energy is conserved and stuff, and things look the same in different bases. So that alone, I think, is a reason to use this machinery, that it bakes in the underlying physical laws, which we still respect, hopefully, in science. And the final thing is that there's also the possibility that if you implement these physical laws, then what comes out is going to look more like physics and is going to be more interpretable.
Thank you. Anyone else with a question? I'll just slip one in.
Yeah.
Have supersymmetric neural network or neural networks that are equivariant? You can use them to design using the Poincaré group to track elementary particles. You'd be tempted as a particle physicist to think that supersymmetric equivariance could be interesting. Is that doable?
I think so. I think that people have been working on it. Yeah, and not me personally, but I think that that's something that's already happening. Yes.
Okay. Very good. So before we thank Risi again, let me remind you that we have another seminar in this series next Friday, not Friday this week, but Friday the other week. We hope to see you there. Remember to take your garbage out of the room. We appreciate you for that. And on that note, let's give a hand again for this very nice talk that we've received. Thank you.